All right, so what I'm going to do today is something very important. I should say the most important topic in your entire learning history of Hadoop. Uh, not so the learning, but yeah, like kind of the most important concept that you should know when you're talking about Hadoop. This is called yarn actually. And if I have to introduce yarn to you, I have to tell you something else. So the problem is not the problem. Last class, I think we have seen MapReduce. I mean, in a rough way, we have seen what is MapReduce, how it works, kind of things. There is this mapping, reducing faces, and you run the program, the mapper program, reducer program, and you get an output. And all these things we theoretically saw. All right, that's good. Theory is good, but what about practical? Like in real world, how does this happen? Like if I simply submit a program to my Hadoop cluster, will it run and give me an output automatically? Well, I don't think so. I don't think that's a good explanation, right? So what happened was that, so we have to understand a little bit of history as well at this point. We had something called Hadoop 1.0, which I am not discussing because that's not part of the syllabus, but you need to actually know something about Hadoop 1.0 if you want to understand yarn and other aspects. Okay, so let me write it here. Yeah, so where is the pen? Yeah. So we had the Hadoop 1 first, 1.0 we call it. And now what we use is Hadoop 2. Most of the companies have moved into Hadoop 2. But in Hadoop 1 and Hadoop 2, the way you store the data is same. I mean, HDFS is exactly same in Hadoop 1 and 2. Of course, in Hadoop 2, you have some extra features added, like you have the snapshot feature of HDFS, you have federation, you have high availability. We will discuss all these features. But the basic idea behind storage or HDFS is same in Hadoop 1 or Hadoop 2. Like you have the block size, you have the replication factor, you have the file system, you have a name node, you have a data node. All this is exactly same, no difference. So whether you are running Hadoop 1 or Hadoop 2, the storage doesn't make any difference. In fact, you cannot even know whether you're running Hadoop 1 or 2 by looking at the storage because it's the same. And that is one prime reason it's really easy to upgrade the storage from Hadoop 1 to Hadoop 2. There is not much upgradation happening, to be frank. So the storage portion of Hadoop is perfectly okay, whether you use 1 or 2. But when it comes to the processing part, we have not discussed processing so far. What we discussed was MapReduce. That is a programming model, but not the processing, right? So if I have to discuss the processing, let me delete this, erase this HDFS thing so I can discuss this. Yeah, quite good eraser we have here. Yeah. So in Hadoop 1, so first we need to understand Hadoop 1. In Hadoop 1, how the processing used to happen was that, you see, we have these data nodes, right? So we all know that what? These are all data nodes, slave machines, right? DN, 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 we call it as data nodes. There was a separate machine called job tracker. Job tracker. So it is a separate machine altogether. It is not your name node. It is not your data node. It is a separate machine, a completely different machine, a very powerful machine called job tracker. Now remember, this is in Hadoop 1. Okay, so I'm just giving you a little bit of history so that you can appreciate yarn, right? So we had this thing called, give me a moment. Oh my God, Deepika Padigon is calling me. Should I be answering? I don't know. Yeah. So we had this job tracker machine in Hadoop 1. So why do you need a job tracker machine? That is the first question, right? So if I create a map reduce program, let's say you have your program, right? So this is your program. You have your map logic, you have your reduce logic, everything. Ultimately, it's a program. It is line of codes. It's a jar file, for God's sake. It's a program, right? You can actually see the program, right? Now, how do you execute this program is with the help of job tracker. So what you do is that this program will be submitted to this guy, job tracker. So job tracker, and that is called a job. So when you submit a program to the cluster, that's called a job. That is why the machine is called a job tracker. Okay, so you submit the program to the job tracker. No matter wherever you submit in the cluster, it goes to the job tracker in that way. Now, what does the job tracker do? The job tracker reads the program. It will not read line by line, but yeah, it reads the program and makes sure that the basic stuff all are there in the program, right? And then it will also look at the program, and in the program, you could have mentioned that you want to run the program on one particular data set, whatever data you have, right? So that means it is the responsibility of your job tracker to figure out where is your data, first of all. So maybe your data is in data node 1, 2, and 3. So what the job tracker does, it understands, okay, so part of the data is here, part of the data is here, and part of the data is here. How does it know? It contacts the name node. Of course, when you get a file name, the job tracker in turns contacts the name node and come to know that, oh, okay, so it is split into 3 or 4, whatever, and it is here on these data nodes. So that means the map program, right? Remember our map reduce example? The map program should run on these 3 data nodes. Right now, it's easy to say theoretically that yeah, the map program goes to every node and runs and gets a result, but practically somebody should do it, right? Somebody should ensure it happens. That is your job tracker. This guy copies this map program to all the nodes, wherever you have your data, right? And it asks somebody called task tracker. There is a guy called what? Task tracker. The task tracker is there on every data node. Okay, so job tracker in turn evokes the task trackers on the data node wherever you have your data. It calls the task trackers. It asks like, hey, take this program, run it on your node, and give me the result. So in a nutshell, if you ask me like what are the responsibilities of your job tracker, the job tracker accepts the job, point number 1. It figures out where is the data, point number 2. It also calls all the task trackers on these nodes and assign them the job to run, point number 3. It then monitors all these task trackers, point number 4. For example, maybe there is a task tracker who runs half the way, it crashes. I don't know. So what should I do? I should restart it, right? So it monitors the life cycle of these tasks that are running. And if they complete successfully, it collects all these data from different task trackers, combines them, and give you as a result. Now, this seems like really nice, happy kind of thing, but it is not so happy, in fact. Why? Because in a production cluster, you will have tens and thousands of jobs running. Imagine, like if you run, let's say 4,000 jobs, that means a single machine, a single job tracker is monitoring 4,000 jobs, and each job may have, let's say, 10 task trackers. So that is like 40,000 task trackers are getting monitored only by the single guy. So the job tracker is actually overburdened. So that is point number 1 you need to understand. Point number 1, the drawback of Hadoop 1 in processing terms is that since you have a single job tracker to monitor all the task trackers, right, and to execute the job, collect the output, make sure it runs, if it crashes, restarts, all these things are done by a single job tracker, and you keep on submitting jobs to the job tracker, right? One job over, another job comes, another job comes, another job comes, and there is no backup job tracker. There is only one guy. Right? So that means the job tracker is actually a bottleneck. It's a performance bottleneck. After a certain time, your jobs becomes too slow. Why? Because job tracker is unable to manage this all these tasks that you are giving. Then you might ask, like, why did you design it like that way? That was the design with Hadoop one. We don't have any choice. You have only job tracker and task tracker, right? So this is the way the what you say programs or jobs are executed in Hadoop one. You have a job tracker, task tracker system, and job tracker will call whichever task trackers it want wherever the data is there, and ask them to run the code and give the output. But the entire, so all these phases that we have discussed in the map reduce, like, map task, shuffle, sort, reduce, then the output, everything is monitored by this single guy called job tracker. So that became kind of a problem with Hadoop 1. So in Hadoop 2, this has been redesigned. So we don't have to actually learn about job tracker and task tracker, okay? Because job tracker and task tracker are part of Hadoop 1. But I'm just giving an idea so you can understand why we have a different architecture in Hadoop 2, right? So point number 1 is this performance bottleneck. Point number 2 has nothing to do with this job tracker or task tracker. Point number 2 is a completely different concept. Now, are you guys following along with me? Are you understanding what I'm saying? Yes, no, maybe. You got what I'm saying? Okay, so I'm getting a chat. Yeah. Okay, great. Good to know that. So this was one problem. This is an architectural problem. This problem is based on the architecture of Hadoop 2. Sorry, Hadoop 1, like the job tracker, task tracker architecture. That is the problem here, right? For example, if we had multiple job trackers, maybe that is good, right? Or we've had some sort of a scheduling or management, maybe that is good. So this is an architecture related problem with Hadoop 1, right? Now, what is the second problem? And the second problem, or a problem which is kind of more bigger than this, is, let me clear my drawing. Okay, is, see, in Hadoop 1, there is a major drawback. Now, if you want to understand the drawback, what you should do is, again, I'm drawing like 4 data nodes. Yeah, 4 data nodes. Now, these are 4 data nodes. Imagine Hadoop 1. In Hadoop 1, the problem was that whatever you do with the cluster, everything had to be a map reduce job. Now, you might think that that's good. That is what you were talking the whole last class, right? No, 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 no. There is a catch here. See, what is a MapReduce job? MapReduce is a programming model where you code, and based on that code, you analyze the data. Fine. But let's say I am a company. I'm the owner of a company, and I am into big data stuff. So I have, like, let's say 1,000 terabyte data in my cluster. Okay, I have 1,000 terabyte data. Now, if I want to analyze the data, that means I must write a MapReduce program. There is no other choice for me. Whatever I want to do with my cluster, I should depend on MapReduce. That means I should hire guys who know Java, because Java was one of the most popular implementations in MapReduce. Like, most of the folks used to write MapReduce programs. That means I should have people who know Java if I want to analyze my data. That's kind of a restriction, right? You cannot say like that, right? Because my data is different, the program is different. I have lots of data. Maybe I want to analyze in a different way. Maybe I don't want to use Java. I hate Java, maybe. There is no choice. You must learn Java. You must code in MapReduce. So initially people went crazy because everybody wanted to learn Java, and then they thought like that is not possible. Then came these tools, like you have this Hive. For example, there is a tool called Hive. You could have heard about Hive. Now, what is Hive? Hive is like a SQL like language, SQL database, right? So what Hive basically does is that if I am a DBA guy, database administrator, I can write SQL scripts which Hive will convert into MapReduce job and run in my cluster. But remember, there again, ultimately, it is a MapReduce job. Are you getting my point? So people came up with other tools like Hive, Peak. So a lot of other tools came. So when you use Hive, what happens is that if I am a database guy, DBA, Hive is very good for me. Why? Because Hive has a query interface where I can write my regular RDBMS queries. I can do a select star, create table, delete table, whatever I want. And in turn, what Hive does is that it takes these queries, convert them into map and reduce codes and run it on the cluster and give me the output. So basically, I don't have to learn Java. I learn my RDBMS language, I can work with Java. But again, that is a limitation because ultimately Hive is converting your queries into MapReduce jobs. So in Hadoop 1, whatever you do is a map and reduce job. There is no other option. So remember the concept we talked about MapReduce. You have the first phase of mapping, then the shuffle, then the sort, then the reduce. This has to be there in Hadoop 1. That is not good. What if somebody want to do something else with the data? I don't want to use map or reduce or nothing. And this also created another problem. That means every data node or every slave node, we have resource, right? What is resource? Resource means processor, memory, hard disk, all these things. So imagine this guy is like 4 GB RAM. I'm just giving a random example, okay? This is 4 GB RAM. This guy is 8 GB RAM. Okay, so these are the resources we have, right? Again, here you have 4 GB, here you have 8 GB. So with Hadoop 1, since you have only MapReduce, these machines will either execute a map job or a reduce job. Correct? Either they'll be running a map job or they'll be running a reduce job, right? So if you run a map job, let's say you're running a map job, you need at least 1 GB of RAM for one map job. For reduced job also, you need close to 1 GB RAM. So that means if this machine is having 4 GB RAM, it can run maybe 4 map jobs or 4 reduced jobs. That is a capacity. And most of the map reduce jobs reserve this capacity. I mean, they will say that, okay, this machine is having 4 GB RAM. Okay, so that means 4 map jobs can run, and maybe only 2 map jobs are running on that machine. Then 2 slots are wasted. 2 GB RAM is wasted. And maybe on some other machine, it has 4 GB RAM. It actually need to run 8 jobs. So actually, it is a bottleneck. So you see, there is no comprehensive planning or scheduling for jobs here. So whichever jobs come first, wherever you have, it keeps on running. That's it. No resource allocation, no resource monitoring, no analysis, nothing. You have a job tracker, you have a task tracker. That is the only thing you get. And the job tracker keeps on, accepting jobs. It keeps on calling task trackers. So sometimes what happens, so another interesting fact is that, look at this second machine, which has 4 GB RAM. This is 4 GB RAM, right? Now, this machine will have lots of data. Maybe somebody will submit 10 jobs and all 10 mappers need to run on this, 10 mappers. But 10 map tasks cannot run on this because it has only 4 GB RAM, right? 4 GB RAM means only 4 map tasks can happen, right? So what happens? Remaining map jobs will wait in queue. It will already mess up. So nobody was there to manage or monitor any of this. The resource allocation was completely poor, and job tracker was completely burdened with all these problems. So this was the problem with Hadoop 1. Now you should understand Hadoop 1 if you want to understand Hadoop 2. I mean, especially the yarn part, right? So people thought, like, first concept they thought is like, this job tracker, task tracker thing should not be good and it should be eliminated. We don't want job tracker and task tracker stuff because job tracker is overburden, like we were discussing. And again, you know, if you do that, if you engage job trackers and task trackers, there is no resource allocation. So anyway, the first thing came was that, you know, we don't want job tracker, task tracker. The second thing was that Since Hadoop is a system where you have a lot of data stored. Now, why do we need Hadoop? For big data. What is big data? Loads of data, right? Like not like in megabytes or gigabytes. You have petabytes of data. So since we have Hadoop, which can store petabytes of data, we need a platform which can allow any kind of application to run. It should not be limited to MapReduce. That's the point. So if I come to Hadoop and say that I want to run my own application, I want to create an application and I want to run my own application on Hadoop, it should allow me to do it. So based on all these concepts, your yarn was created. So the result is called yarn. So in Hadoop 2, the processing part is called yarn. In Hadoop 1, the processing part is called nothing. Actually, it is called job tracker and task tracker. That is only way they call it. In Hadoop 2, the same processing part is called yarn, Y-A-R-N. Let me clear the drawing. So it's called yarn, Apache yarn in fact. Yarn stand for yet another, come on. Yeah, yet another resource negotiator. Yeah, so the name of yarn is yet another resource negotiator. Now, from the name itself, it is pretty clear that this has something to do with the resource, right? So there is something to do with resource, right? Let me say I'm getting a chat. Ashok is asking any other tool similar to Yarn. No. Yarn is not a tool actually. Yarn is a platform, just like HDFS. Like HDFS is the storage part of Hadoop, right? So there is nothing like HDFS because everything is on top of HDFS. Same like that, the processing framework is called Yarn. And you can have multiple tools on top of Yarn, right? So Yarn is a framework actually created by Apache to accommodate all sorts of processing on Hadoop, right? And Yarn is called yet another resource negotiator. So from the name itself, it is clear that this has something to do with resource and negotiation. And exactly that is what Yarn does. It does resource negotiation. So any questions you have? I'm getting some questions. Any other framework to manage Hadoop cluster? No, there is no other framework. Why? Because see, so what is a framework? See, Hadoop itself is a framework, right? So when you say Hadoop, what is Hadoop? Hadoop is a framework, right? So in Hadoop, the storage part is handled by HDFS. When you talk about Apache Hadoop, okay? And the processing part is handled by Yarn, right? When you talk about Apache Hadoop. Now, you can ask like, is it always the same? I'm gonna say no. Why? See, whenever we say Hadoop, we actually mean Apache Hadoop. In Apache Hadoop or the open source Hadoop, in Hadoop version 2, the storage is always HDFS. The processing is always Yarn. There is no difference. Nobody can replace Yarn. Nobody can replace HDFS. But when you go to Cloudera, Hadoop, again storage is HDFS, processing is Yarn. No problem. When you go to Hortonworks Hadoop, again storage is HDFS, processing is Yarn. But remember this, when you go to MapR Hadoop, storage is not HDFS. Now we have a separate session on MapR, and I will explain that when MapR comes, but I'm just, yeah, you have something called MapR file system, MapR FS. Okay, so MapR does not actually follow the traditional rules of Hadoop. I don't know why. I hate Mapr personally. Mapr is the company I hate the most because I don't know. Maybe they are one of the most popular companies in the world or something. I hate them. Like I don't even listen to the lectures at all. I mean, they have completely rebuilt Hadoop and they call it as Hadoop. There is no name node. Okay, point number one. Look at the architecture. There is no name node. Okay, there is no HDFS. I think Yarn is there, and they call it as Hadoop. Now, who want to call it as Hadoop? I don't call it as Hadoop, but since the sake of teaching, I teach Mapr. I mean, yeah. So, I mean, I cannot deviate from the technical aspects of Mapr, right? So, Mapr is a good platform, but I personally hate it. Why do you want to screw up such a good platform? I don't know. They claim that this is the best, HDFS is the worst and all other things. I hate them personally. But yeah, my technical point is that when you go to Mapr Hadoop and when you search for HDFS, you will not find HDFS. So there is no name node, no data node. The concepts are same. Rather, you have MapRFS. The file system is a fully POSIX compliant Unix based file system that they have developed. Some sort of that. I think Yarn remains the same with Mapr also. I'm not sure, but yeah, Yarn remains the same. But yeah, HDFS side is completely revamped. So to answer your question, Ashok, yeah, Yarn remains the same, I believe, almost in all the architecture. Okay, now let's have a brief look at the Yarn architecture, so we'll understand how it is. Any questions you have, you can ask me, no problem. It is actually very difficult to explain Yarn because it's kind of a very complex system, I must say. We can explain. It's not like I cannot explain. Shoki is asking what other file system we can use with Hadoop. That's what. With Apache Hadoop or Cloudera, you use only HDFS. There is no other choice. But with Mapr, it is MapRFS. You can use any file system you want. Anything. You can create your own file system and use it if you want. Because Mapr file system is called MapRFS. It's a POSIX compliant general file system, generic file system, which you can use. So Mapr has developed that so that people can actually use any sort of file you want. So that's the difference. When you use Mapr Hadoop, you can use that cluster simply as a storage device. It need not be part of Hadoop. Are you getting my point? When you run Mapr on Hadoop, what happens is that, can we use S3? No, not on premise. If you run on cloud, maybe, yes. You mean simple storage service from Amazon? Is that what you mean? S3? In hybrid model, I don't think so. No. Yeah, so see, what is a file system? Somebody should develop a file system, right? We cannot actually use our own file systems, right? Like I cannot maybe use NTFS. NTFS is a file system, right? So I cannot maybe use NTFS myself. If Hadoop allows me to use it, I can use it. So typically what happens is that, typically it is HDFS everywhere you go. Wherever you go, typically it is HDFS, Hadoop Distributed File System. 99% of the people will be using HDFS, I believe. Only exception is that when you are running Mapr, okay, when you run Mapr, you have Mapr file system or MapRFS, where you can store your files. Apart from that, I think mostly they run HDFS, okay, for storage. And processing, if you are running Hadoop 1, then it is different, like you have job tracker, task tracker kind of thing. Hadoop 2, it is always Yarn that we prefer. Okay, but that's what I don't know completely. So maybe there is a company. So that is another advantage, right? Apache Hadoop is open source, right? So if you are a good developer, maybe you can download Apache Hadoop source code and create your own Hadoop. Maybe you call it as Ashok Hadoop. I don't know. I mean, yeah, let's say you develop Hadoop. You call it as Ashok Hadoop. And you say that, hey, I have found that you can store your files in NTFS. or NFS maybe, for that matter. NFS is already there, supported. Okay, but yeah, so you can make your own changes and call it as your own Hadoop. That's what open source is, right? And that's what all these companies are doing. And I'm not sure, maybe there is a company who supports all the file systems. As far as my limitation is considered, or my expertise is considered, I am familiar with Hortonworks, Cloudera, and Mappa. They don't use anything apart from this HDFS and MapRFS. Apart from that, they don't use much. Right? No, it's good. Like, yeah, Ashok, it is good that you brought up the point. So otherwise, no, we discuss only whatever is there in the syllabus, right? It's good that you ask the point so we can discuss something like this. It's always good. Otherwise, I just say that, yeah, there is HDFS, that's it. You believe it and that's it. Okay. I will do one thing. It's like 4:15. Why don't we take a quick break? I just need a small break. Be right back. Then we will continue with the yarn architecture. Don't worry. We'll take a small break and be right back. Okay, so we were discussing yarn, right? Let me see where we are. So the main idea behind yarn is to negotiate resources. Okay, to understand this, in yarn also you have a master machine and slave machines. Like the master machine is also called resource manager. So this guy is called resource manager. And on every data node, you have something called node manager. Node manager. So NM. So NM stands for node manager. So the basic idea behind yarn is that you have a master machine, a separate machine called a resource manager. This looks like job tracker, but it is not job tracker. Okay. So you have a dedicated independent machine called resource manager. And on every data node, you have a daemon called node manager. Now I will tell you what are the responsibilities of all this. But before we understand this, let's analyze one thing. So let's say that you have a data which you want to analyze, and the data is actually on data node 2 and 3. So the data is split into multiple chunks, and the blocks are stored in data node 2 and 3. So this is data node 1, this is 2, and this is 3, right? So now let's say you submit a job or a program to analyze this data. Now the program obviously goes to resource manager, right? So this is the guy who accepts your program, right? So this resource manager accepts your job or program, whatever it is. And then what happens is that, so the resource manager is connected to all the nodes. Okay, so I just want to draw this. Yeah, it is connected to all the nodes that we have. The resource manager will contact any of the node manager. Now this is really important. The resource manager will contact any node manager in the cluster. It need not be the node manager which has some data or nothing like that. So in this example, let's say this guy contacts the first node manager, first data node where you have a node manager. It will call the node manager and say that there is a job. Now what the node manager on that machine do is that it will launch a daemon called application master. We call it as app master or application master. Now the node manager launches this application master on the same node, like on the data node 1. So remember, the job was given to resource manager. Your data is in data node 2 and 3, and resource manager contacted node manager 1, which is on the first data node. The node manager, whenever it gets to run a job, has to launch something called application master, or we call it as app master. Now this app master is per job. That means if you submit one job, one application master. 3 jobs, 3 application masters. So in my example, I have submitted only 1 job. So the node manager launches something called application master. Now, it is the responsibility of this application master to run the job. Now, what the application master does, this guy, application master, can contact your node manager as well as it can contact the resource manager. This is important. Your application master can contact node manager because it is on the same machine. It can also contact the master called resource manager. It has communication both the ways. So by contacting the resource manager, the application master comes to know that, the data is actually in data node 2 and 3, not on itself. Like this guy got launched in data node 1, but your actual blocks are on data node 2 and 3. So what the application master does is that this guy will contact these 2 nodes, okay, and will launch something called container. This is called a container. This is called a container. So this is a container and this is a container. What is a container? A container is a simple Java process or a JVM, you can call it. And inside the container, your program will get executed. So if it is a map reduce program, the map job, reduce job, all will get executed within the container. Now you might ask, like, what is the advantage of such a complex architecture if you do something like this? The advantage here is that the resource manager, so what is the purpose of your resource manager? Is it only used to simply call a node manager? No. Now let's say that these 2 containers are running, right, your jobs, and if these machines need more resources, more RAM, more processing power, the app master can contact the resource manager and ask it to allocate resources. So the resource manager is a global entity which handles the entire resources, RAM, processing power, etc. So whenever an application master needs more resources, it can contact the resource manager and the resource manager can allocate more. On the other hand, the entire life cycle of the applications, starting from creating the application, terminating it, monitoring it, everything is done by app master. So the burden is actually reduced from resource manager, right? Now I'll take some questions because it's quite difficult to understand in the first run. So Bharat is asking, what is the difference between node manager and data node? Yeah, node manager and data node are different daemons. Remember, data node is used for storage. It's the same machine. So basically all these things are processes like Linux processes or Unix processes. So on your slave machine, right, where you have your hard disk and other things, right? You run a daemon called data node, which will handle the storage. You run a daemon called the node manager, which will handle the processing. So that is a difference. The data node daemon is responsible for handling your blocks. The node manager daemon is responsible for handling your application, how it actually runs. Okay. Yeah, so I can unmute you folks one by one if you want. Ashok says Ashok has some queries. So I will first unmute Ashok. Then we'll unmute others also. Don't worry. So give me a moment. I will unmute Ashok first. Yes, Ashok, please.
Yeah. Hi, everyone. Raghu, I have 2 to 3 queries, which is point to point. Number 1.
Okay.
Whether we have only one app master on node 1 or whether there will be separate app masters will be on separate nodes.
Yeah, so the question is that when an app master will be launched, right? So the app master is actually launched by the node manager. You can have multiple app masters if you want, but what you need to remember is that app master is just a daemon. And that guy's responsibility is to execute your job. And the app master in turn launches these containers wherever you have your data. You can have more than one app master. No problem.
Okay.
Then
Yeah. I'm just I forgot my next question query. Okay.
ask, no problem.
No. And it's, see, obviously, data node will also having a separate JVMs on on each nodes, right? All these three nodes. Data node will be a separate process. That is
Data
basically
node
a
is a data node is a separate process which handles only storage. Actually, data
yes.
node has nothing to do when it comes to yarn because it just simply stores the data.
Yes. You are right. And I can put on the same machine where resource manager is there. I can use the same machine as a name node also. Or you want me to use name node on a separate machine?
Ideally, in production, this will be different. Like name node will be different and resource manager will be different. Why? Because both machines are taking a lot of load actually. So when you think about name node, like in
Hmm.
production clusters, you have millions of blocks. So a lot of metadata, a lot of what you say, requests to read and write. All this is done by your name node. So if you include the resource manager also on the same machine, maybe the performance will get degraded, but it is not impossible. Like in labs and all, we always do that. You can run resource manager and name node on the same machine very much, no problems. Like
Now,
if you
one important. Yeah, I got
uh,
it. One
uh,
more point from admin perspective.
uh,
Um, if I am a administrator, for example, I have to process 1 petabyte of data. Okay,
okay,
and I have a blocks of 256 MB.
okay.
So, what should be the optimum size of my machines in terms of resources, which I have to utilize that? Which is the right
Yeah,
or optimum best case or average case, you can say, and what
yeah,
the worst case is obviously lost.
yeah. We have a separate module actually on planning, but
Okay.
since you have asked, uh, hard disk capacity is completely up to the administrator because the hard disk capacity determines like what is the actual storage, right? So let's say every data node is having 12 terabyte hard disk, 12 TB, for example. So if that is your configuration, then you have to think how much data you're getting every day or every week, and what is your replication factor, because data will be multiplied by replication factor. And then you have to plan that whether you should buy extra what you say nodes or what, from a storage perspective. From a processing and RAM perspective, we have a slides, but what I have seen practically is that data nodes will be typically 32 GB RAM minimum, and name node and resource manager 64 GB plus RAM size. The processors will be usually quad core or more than that, Xenon. If you're using
But
Intel, Xenon.
I
Yeah.
have query because I don't think because it's a pure JVM play. So
Hmm.
if it is a JVM play, I think CPU usage won't be increased, but RAM usage will be increased drastically.
CPU usage will also be increased because CPU is actually burdened in different ways. For example, you have processes which are copying data, you have applications which are executing data, and also your host operating system is using data. So CPU utilization also takes place, but not in a very high way, I should say. That is that is why
Yes.
you have like quad core processors, like
Yes,
quad
because
core is.
yeah, you are right, Raghu. Actually, JVM heap size matters most
Hmm.
because I am basically working in Java only. Okay,
Oh, okay, okay.
so that's why I know that because we prepared migrations also and migration from one content system to another content system where
Uh-huh.
JVM heap size matters most.
Yeah, right, right. And one
CPUs,
more very interesting thing is, since we brought up this discussion, see, when people invented Hadoop, what happens is that, let's say you are running Hadoop. Actually, where is your data? Your data is on hard disk. So when I am processing the data gets copied from the hard disk to the RAM. Of course, that happens. And then the execution happens, and it is slow because like any other system, when you have your actual memory in the hard disk, then it comes to the RAM and then gets processed. It tends to become really slow. That is the reason we have tools like Spark. So
okay.
Spark is the competitor for Hadoop. Not competitor, but yeah, like Spark is gaining a lot of interest these days. Why? Because Spark is pure in-memory processing. Everything is in the RAM, no hard disk needed. You need hard disk, but very minimal. Everything that you do is in RAM, in-memory processing. So it is like 10 times faster than Hadoop. It has its own disadvantages, cost factor, instability, but comparing the speed, Spark is much faster than Hadoop.
No,
So that
but
is
there is,
one place.
yeah, yeah, you are right. But in Spark, there is another concern also because Spark uses majorly FS disk. They never uses SATA
Yeah, correct,
because
correct,
SATA is at 1/10 speed of FS disk.
correct, correct.
So, so this is
So
the actually major concern.
we rightly pointed, we so many use cases of Spark, and there are a lot of advantages, a lot of disadvantages, but ultimately people want speed sometimes, I want
Yeah,
real time, I cannot wait. So those are the times when sometimes people actually look for these kind of in-memory solutions. But with Hadoop, so Yarn is actually a platform, I should say, which aims to do this. Now, the second biggest advantage of Yarn. Now, first advantage is what I said, like this architecture, like you have separate resource manager, app master, container. The second biggest advantage is that it can run any type of application. It need not be MapReduce. That is a real catch. Why? Because there are a lot of companies. For example, there is a tool called Giraffe. Anybody working on Giraffe? No, right? You heard about Giraffe? I don't think
I
so.
heard of, but it is not. It's a kind of database which stores
Ah,
graphs kind of data.
graph processing, exactly. So Giraffe is graph processing. Then you have Tez. It is from India. Some folks in Delhi developed it. Tez, T-E-Z, Tez. Tez is streaming data, real-time streaming data. So, so these tools like Tez and Giraffe, they can actually use Yarn. Why? Because when you are working with a Tez or Giraffe, it is not MapReduce. They don't follow MapReduce at all. They have their own ways of processing, and Yarn actually supports it. So the biggest advantage
Okay.
when you implement the Yarn is that your jobs in Hadoop need not be MapReduce jobs. You can write your own jobs if you want, like streaming data or other type of data. Whatever graph processing, visualization, whatever
Yeah.
type of analytics you want to do with your cluster, you can do it. And for Yarn, everything is an application. Like we saw that the application master launches containers. So inside this container JVM, either it can run MapReduce task, traditional, or it can run something like Tez or something like Giraffe or something else, anything. And the biggest advantage, like I said, was that the resources are managed beautifully. Since you have a central resource manager, it can allocate the resources whenever you want, not like in Hadoop 1. In Hadoop 1, like I said, it is predefined. You have some machines, there is map slot, reduce slot, nothing else. Either it is map or reduce. Sometimes a machine will be sitting there with 64 GB RAM. Nobody will be using it because there is no data on it. Nobody is interested. Map slots are wasted, resource reduce slots are wasted. But here the resources are not controlled by your data nodes. It is controlled by your resource manager. So this guy decides, okay, take the data, go to that machine, process it there because it has more RAM or maybe more processing power, whatever you want, and give me the result. So this way Yarn has actually revolutionized. And I was actually teaching Hadoop for like I don't know, quite some time, for past 5 years or something. And like quite frequently the syllabus changed, like 6 months back. mm, Before that, before 6 months, the syllabus was like we had Hadoop 1 and Hadoop 2. So I'll start with Hadoop 1. I will explain Hadoop 1. I will explain job tracker. I will explain task tracker. We will configure Hadoop 1 cluster, then go to Hadoop 2. But recently, the syllabus was modified. Why? Because Hadoop 1 is quite old. Nobody uses it. So why should we spend time on creating a Hadoop 1 cluster? That is not needed. So we no longer discuss job tracker or task tracker, but I think it is really important to discuss it, because then only you will understand why Yarn is having this advantage, right? So anyone else has anything to discuss? I'm more than happy. Yeah, so Guru Balakrishnan, let me unmute you. Yeah, please, you can speak.
Hi Raghu, hi everyone. Raghu, as you mentioned, like app master will have the container component, right? That container component will run the all the jobs which we submitted.
Yes, yes.
So the container is like it's like a process, or it's how it's like
Yeah, it's a
what?
JVM basically. Container is a JVM actually. Very
Okay,
simple. So container, we call it as a Java process, and that is responsible for executing that what you say, a map job or reduce job or any sort of job that you're submitting to the cluster.
okay. Correct me if I wrong. Example, if I given the job to the resource will check, launch the application master from node manager, and that
Yes.
application master will check where is the data.
Uh,
Then that will launch the container, and whatever job I
exactly.
submitted, whatever job am I submitted, that will be processed in the container. Then it will back to the application master, and it will go to resource manager, and you will get the output. It's am I right?
Exactly, exactly. You are exactly correct. And here the synchronous job is between application master and resource manager. So once the node manager launches an application master, its job is done. Node manager's job is done. Not done. What node manager does is there is one more responsibility for your node manager. The node manager is on a data node, right? So it keeps on monitoring its resources, like how much RAM I have, how much is used, how much is free. It sends this record back to the resource manager. That is how resource manager knows, how much free RAM you have. So node manager is responsible for monitoring itself, the resources, and reporting back to the resource manager. But ultimately, when the jobs are executed or your applications are executed, it is the application master and the resource manager who negotiates for resources and execution parameters, whatever you want. And once the job is completed, the application master will tell the resource manager it is over, and it will destroy itself. So an interesting fact is that these daemons, I will practically show you this, don't worry. Like it's not like I'm reading some theory paper or something. I'll practically show all this, but yeah. What you can see in practical is that if you look at a cluster where there is no job running, you will see only resource manager and node manager. Nothing else will be there. But the moment you submit a job, what happens is that automatically your app master will be created. Then you can see the containers. The container has a name called yarn child. I will show you that. Okay. So the container will have a technical name. It is called yarn child. I mean, it's like a child process basically. So we see all this and we can see that, yeah, the jobs are getting executed. Now, one more important component here is that, which I didn't discuss. Yeah, so did I answer your question? I forgot to ask.
Yeah, Raghu. And one more thing, like
Yeah,
if
please.
I in this explanation, right, we have three nodes. It's mandatory to install or configure the node manager and all the three cluster and apps master every node.
Yes. Now, App Master, you don't have to configure. It gets created automatically. You have to
Okay.
configure Node Manager on every nodes. Because
Okay.
ideally, that is a situation. Like, it is a client. So
Mhm.
to better utilize your cluster, ideally, you configure Node Manager on every data node.
Okay. Okay.
Okay.
Thanks.
Yeah. So one more thing that I forgot to discuss, not like I forgot, but I was planning to discuss is that Ashok has a question, I think. If resource manager fails, how it will connect to existing node manager? Yeah, you can have a backup for resource manager. That is not a problem. The resource manager can be configured in an active standby mode. Like you can have multiple resource manager. I mean, only one will be active at one time, but you have a hot standby. That is possible. If it fails, the other guy will take over. Now, one thing that we didn't discuss so far is this is the main challenge for an administrator. Now, running a job is not a challenge for an administrator because somebody is submitting the job and everything is taken care by automatically, like resource manager is already configured, app master will get launched, it will run, it will get the result. Being an Hadoop administrator, you don't have to worry about how a job is running. But let me tell you where you actually get really stuck. I mean, I have discussed this with many people, real-time admin guys, and they say this is the greatest pain in their entire life. So I'll tell you what it is. It's a very so Ashok is asking how to cluster both RM. I'll come to those details, Ashok. We have not discussed the architecture. There is a option to cluster them. Okay. Now, the biggest problem that we have in a cluster is not running the jobs or resource manager. These things all will happen automatically. But let me tell you what is the biggest problem. It's easy to understand. Let me delete this annotation. Okay. Yeah. See, when you say I have one cluster, okay, what do you actually mean is that maybe I have 100 data nodes, right? Imagine your cluster is having 100 data nodes. So you have 100 data nodes, and just for the sake of argument, imagine every data node has 4 GB RAM. So the total capacity is 400 GB RAM. Now you should look at the capacity as a whole, not like on one data node, right? So 100 data nodes you have, each data node has 4 GB RAM. So total capacity is 400 GB RAM. Now let's take a very plain example of MapReduce job. I'm not going to graph processing or something else. If I launch a MapReduce job, one map task will take 1 GB RAM. One reduce task will take 1 GB RAM, right? And if I have a really large data, which is split across multiple data nodes, on every data node, one mapper should run, right? So that means if I'm running 10 mappers, 10 GB RAM is gone. Now you're getting the problem. The problem is that what if 1,000 people come to your cluster, submit 1,000 jobs? What will happen? That is a nightmare of every Hadoop administrator. See, I am a developer, you are a developer, and the other guy is a developer. We are all working on the same cluster, right? We all come and submit one jar files. What will happen? The resource manager will get, let's say, 1,000 jar files. It will execute 1,000 jar files, but the problem is that your cluster's capacity is less and you are submitting more jobs. Now, what will happen? The jobs will happen, it will not fail. Okay, so by default, what happens is that you have something called a FIFO scheduler. So there is a concept called scheduler. By default, there is something called a FIFO scheduler, or first in, first out scheduler. Now, what is a scheduler? A scheduler is a part of your resource manager. So since resource manager handles resources and jobs and all these kind of things, it also has a component called scheduler. So what does scheduler do? It schedules the jobs in simple ways. So if you do not configure anything on your cluster, you run it on the default metrics or whatever you want, the scheduler that works is called FIFO scheduler, or it is called first in, first out scheduler. That means if 100 people submit the job, it will take the jobs as it comes in. 1, 2, 3, 4. It executes the job as it comes in. 1, 2, 3, 4. That is a FIFO scheduler. Now, FIFO scheduler is good on the first look, but it is bad. Why it is bad? Because I am a developer, imagine, and I am submitting a job. And my job, let's say, will take half a day to complete. Now, don't be alarmed. You have jobs which will run for weeks in clusters. Okay, so my job is going to take half day, and it needs the entire 400 GB of RAM. Maybe my data is on all the machines. So if I submit my job, what will happen? I am in fact preventing others from submitting the jobs, because if you are using the FIFO scheduler, unless my job is complete, others cannot do anything. because I'm using all the resources and my job is very complex. It will take half a day. Maybe there is a very important job which need to be run and that can be completed in 5 minutes, but it should wait because there is no other way, because your scheduler is configured in that way. So the point that I'm trying to make here is that the FIFO scheduler or the built-in FIFO scheduler is not so effective in many cases. So to get rid of that, we will have a separate session on that. We have something called fair scheduler and capacity scheduler. Now these are two different schedulers. Okay, both are from Apache. That means they are free to configure, like you don't have to pay money or something. I mean, you can configure them. There is a difference between them. I'll come to the difference later. This is not the right time to discuss that. But basically, using schedulers, what you can do is that you can create sharing of resources like pools. You can say that if 5 users come to submit a job, all 5 of them will get at least a portion of the resource to run, so that they don't have to wait. Or you can say that if 5 users come, they can submit the jobs to a queue. You can have a priority queue where all the jobs submitted will be executed immediately. Then you have a less priority queue where the jobs submitted can wait for some time, like batch processing. So with scheduler, whether it is fair scheduler or capacity scheduler, you can have a fair way of utilizing the cluster rather than having this barbaric FIFO scheduler, which just takes whichever it gets first. So the scheduler is a part of your resource manager, and you have to configure it. You have to tell it that you should run in this port, something like that. And so actually there are 3 components. You have resource manager. Inside resource manager, you have a scheduler. You also have something called a resource allocator. Resource allocator. It is a daemon which actually allocates resources. You don't have to do anything, it automatically does it. I mean, based on the request, it allocates resources. Okay, so schedulers are needed so that when you submit jobs, it can be prioritized. And Cloudera, when you get Cloudera Hadoop, by default, they have fair scheduler. When you buy Hortonworks, by default, they have capacity scheduler. I don't know why, but yes, this is how they do it. Like if I get a Cloudera Hadoop, by default, I get fair scheduler configured. If I get Hortonworks schedule, Hortonworks, Hadoop platform, I get capacity scheduler by default. This is how it works. Guru is asking, in Hadoop 2, metadata resource manager will have standby secondary. You can replicate to another cluster, Guru. Okay, it's not like a standby cluster, but in Hadoop 2, you have a possibility of replication. You can replicate your entire cluster to another cluster if you want. We have a session on replication and other kind of things, and I will definitely have a look at that. Now, let me quickly check at these slides that we have, maybe. Because I was talking, we forgot to discuss the slides. Yeah, I like backup. You have backup option. Yes, you can replicate it. I'm just seeing where we have left the slide. Yeah. So this is what it is, what I was discussing. So these are the components of yarn, not MapReduce. Actually, it is written MapReduce has the following components. No, yarn has the following components. There is a mistake. You have resource manager is the master that arbitrates the available cluster resources. and thus help manage. You have node manager that manages individual computer nodes, app master, the process that coordinates the execution of an application in the cluster. Okay. And this is how MapReduce works. I don't think I have to explain this. We have discussed this in the last class. You have mapper, you have reducer. Map function is applied to every input key value pair. It generates intermediate key. So you can go through this if you want further knowledge. This slide actually shows you how an HDFS, so coming back to HDFS, how an HDFS write actually happens. See, when you ask to write a data, okay, what happens is that the HDFS client will call something called a distributed file system object. It's a Java object actually. This will in turn do a create request to the name node. Because when you want to write some data, you have to contact the name node. Name node is the only guy who can give you the location. Once you get the location, you open something called an FS data output stream. It is another Java object. And what you need to remember here is that, when you are writing data into HDFS, you write only to one data node. You write only to one data node. It is the responsibility of that data node to write it to the second one. And it is the responsibility of the second data node to write it to the third one. That means replication is not your responsibility. Got the point? So when you are writing a block in Hadoop or HDFS, you write a block, fine. So the write completes of a block, then you wait. Why do you want to wait? Because that data node replicates to the second guy, and the second guy replicates to the third guy, and the third guy acknowledges the second guy, second guy acknowledges the first guy, and you get a result saying that, yeah, the writing is complete. Right, so this is important because writes are sequential. And you have an explanation here which you can read. On the other hand, the reads are not like that. That is the difference. When you read a file, you can read parallelly, right? You don't have to read one block, second block, third block. Maybe you can read parallelly. If your system is so powerful and if you have enough bandwidth, you can read blocks parallelly if you want. So writes are sequential, reads are parallel. Remember this point, okay? And we call this as pipelined write. So this concept is called pipelined write. So what do you mean by pipelined write? That means you write to one data node and there is a pipeline of data nodes lying just after the first data node which replicates the data, and every one of them gives you an acknowledgement saying that yes, we got the copy. Then your writes are completed. Getting the point? So that actually finishes the second module.